focus. Reactions involving gases. So sometimes we have a gas as a reactant or a product, and so then we can't really use molarity to express the quantity. We need to use the temperature, the volume, and the pressure of the gas. We can't use mass conveniently either because gases are difficult to weigh. So when we're doing stoichiometry involving gases, we will often use the ideal gas law because N is equal to PV over RT, right? So if we know the pressure, the volume, and the temperature, we can calculate the moles of gas, and that's what we need in that mole ratio to find the other thing that we're looking for. If we're finding information about the gas, once we get N, the moles from the mole ratio, then we can use this version of the ideal gas law to calculate the volume of the gas. When the reaction occurs at STP, things are greatly simplified, and we can use our little friend, the molar volume of gas at STP. A mole of gas is 22.4 liters. When we're dealing with gases in reactions, we could also be looking at partial pressures because we might have a mixture of gases. So the basic plan, this was our starting point, grams to moles to moles to grams. So again, the mole to mole part in the middle is the same, but we might be mixing it up at the beginning or at the end. So we could have a gas at the beginning and a gas at the end. We could have a solid at the beginning and a gas at the end. We could have a gas at the beginning and a concentration of a liquid at the end. There are so many possible variations, but they all start with grams to moles to moles to grams, and then just alter that as needed for the problem. Here's an example. In the following reaction, 4.58 liters of oxygen was formed at P equals 745 millimeters of mercury and T equals 308 Kelvin. How many grams of Ag2O decomposed? Well, we have a chemical equation here. We can use that, as we did with other stoichiometry problems, to organize the information. So it's telling me I have 4.58 liters of oxygen. So under O2, I'm going to write 4.58 liters. And it tells me what the pressure is, so I'm going to stick that down there too. Pressure is 745 millimeters of mercury, and the temperature is 308 Kelvin. At least we don't have to convert that. All that information was about the oxygen gas. What are we trying to find? Grams of Ag2O. Okay, so regular stoichiometry, grams to moles to moles to grams. Well, we want to find grams, so the ending here is fine, but we need to change up the beginning, right? Because we have a gas. So this is going to be P, V, and T. We need that information, because using P, V, T, and R, we can calculate the moles of the gas, and then we can go on our merry way. Any questions about that? So to get from this information we have about the gas to moles, we use the ideal gas law. So it doesn't strictly look like dimensional analysis at that point. So first we need to calculate the moles of gas. So we take PV equals nRT and we rearrange it. N equals PV over RT. There's no talk of this being collected over water or anything, so we don't have to worry about a mixture. So this pressure is the pressure of the hydrogen, but it's in millimeters of mercury. We need to convert it to atmospheres. So that would be 745 over 760 in atmospheres. The volume was given in liters. Hooray. 4.58 liters. And then R is always the same thing, 0.08206 liter atmospheres. per mole Kelvin. And the temperature, 308 Kelvin. So my atmospheres cancel, liters cancel, kelvins cancel. This is going to give me moles of gas. 745 divided by 760 times 4.58 divided by 0.08206 divided by 308, 0.1, that's not a 1, 7763, and that's moles of oxygen. Any questions about how we got to that point? This is moles, and so now I'm going to jump into my stoichiometry path here at moles. I'm going to convert to moles of Ag2O and then grams of Ag2O. So 0.17763 moles of oxygen. I don't want to round that yet because that could cause errors. So for moles of oxygen, I'm going to moles of Ag2O. I'm dividing by moles of oxygen, so those units cancel. And then my next step is I'm going to grams of Ag2O divided by moles of Ag2O. Mole to mole, that's a mole ratio that comes from the coefficients in the balanced chemical equation. 2 moles of Ag2O gives 1 mole of oxygen. So I put 2 in front of Ag2O and 1 in front of oxygen. For the molar mass, I'm going to have to calculate that, 107.9. So I've got 2 silvers, 107.9, and an oxygen. So 2 times 107.9 plus 16, 231.8. That's the molar mass of that compound. 231.8. And the moles cancel. So 0.17763 times 2 times 231.8 equals 82.349. This is my final answer, so I can round that. 82.3 grams of silver oxide decomposed to form that much oxygen. Any questions? You see why I wanted you to learn dimensional analysis? When you can cancel units out like this, it makes all the calculations so much easier. If you still are very iffy on dimensional analysis, it's not too late. It's not too late, okay? How many liters of oxygen at STP are required to form 10.5 grams of water? The balanced chemical equation. So this is stoichiometry, grams to moles, to moles to grams. Let's write down what we've got here. We've got 10.5 grams of H2O. And it's asking how many liters of oxygen, question mark, liters at STP. That's an important piece of information. So then we looked at grams to moles to gram to see, well, how should we modify that to fit our problem? Well, this is what we're given. We're given grams. So grams to moles, we can do that. But at the end, we don't want grams, we want liters. So here, we want liters at STP. At STP tells me I can use 22.7, yeah, I can't say it, but I can use it, 22.4 liters per mole. You can only use that at STP. It's tempting other times. So we're going to start with 10.5 grams of water. We're going to convert to moles of water and moles of oxygen, and then liters of oxygen. And we put the previous unit in the denominator, so those are going to cancel out. So I put all the units in there. The units then tell me where to put the numbers. So here, grams to moles for water, that's the molar mass of water. We've calculated that one before, 18.016. Where do we get the mole ratio? Coefficients in the balanced chemical equation. 1 oxygen gives 2 waters. So 1 in front of oxygen, 2 in front of water. The magic at STP tells me I can use the molar volume of a gas. So it's 22.4 liters per mole. So 10.5 divided by 18.016 divided by 2 times 22.4. 3 sig figs, 6.5275. So I would round that to 6.53 liters of oxygen. Any questions? Yeah. Yes, you can use the ideal gas law here. Instead of the 22.4, you can calculate moles of oxygen. Stick that into the ideal gas law. STP tells you what the pressure and the temperature are. Yeah, that absolutely works too. Any other questions? Yeah.
Question about the previous one.
Okay.
So when we calculated trying to find the moles, I got a different answer. I got 0.1808.
You got 0.1808.